the optical transfer function is a complex transfer function where the modulus of the function describe the modulation transfer and the argument of the function describe the phase transfer in an optical system, such as a camera, microscope, human eye, or projector, as a function of spatial frequency. It is used by optical engineers and scientists to describe how the optics project light from the object or scene onto a photographic film, detector array, retina, screen, or simply the next item in the transmission chain. The function specifies the translation and contrast reduction of a periodic sine pattern after passing through the lens system, as a function of its periodicity and orientation. Formally, the optical transfer function is defined as the Fourier transform of the point spread function, or impulse response of the optics, that is the image of a point source. When this image does not change shape upon lateral translation of the point source, the optical transfer function can be used to study the projection of arbitrary objects or scenes onto the detector or film. While figures of merit such as contrast, sensitivity, and resolution give an intuitive indication of performance, the optical transfer function provides a comprehensive and well-defined characterization of optical systems. Definition and related concepts. Since the optical transfer function is defined as the Fourier transform of the point spread function, it is generally speaking a complex-valued function. The projection of a specific periodic pattern is represented by a complex number with absolute value and complex argument proportional to the relative contrast and translation of the projected projection, respectively. Often the contrast reduction is of most interest and the pattern translation can be ignored. The relative contrast is given by the absolute value of the optical transfer function, a function commonly referred to as the modulation transfer function. On the other hand, when also the pattern translation is important, the complex argument of the optical transfer function can be depicted as a second real-valued function, commonly referred to as the phase transfer function. The complex-valued optical transfer function can be seen as a combination of these two real-valued functions, where and represents the complex argument function, while is the spatial frequency of the periodic pattern. In general is a vector with a spatial frequency for each dimension, that is, it indicates also the direction of the periodic pattern. The impulse response of a well-focused optical system is a three-dimensional intensity distribution with a maximum at the focal plane, and could thus be measured by recording a stack of images while displacing the detector axially. By consequence, the three-dimensional optical transfer function can be defined as the three-dimensional Fourier transform of the impulse response. Although typically only a one-dimensional, or sometimes a two-dimensional section is used, the three-dimensional optical transfer function can improve the understanding of microscopes such as the structured illumination microscope. True to the definition of transfer function, should indicate the fraction of light that was detected from the point source object. However, typically the contrast relative to the total amount of detected light is most important. It is thus common practice to normalize the optical transfer function to the detected intensity, hence. Generally, the optical transfer function depends on factors such as the spectrum and polarization of the emitted light and the position of the point source. For example, the image contrast and resolution are typically optimal at the center of the image, and deteriorate toward the edges of the field of view. When significant variation occurs, the optical transfer function may be calculated for a set of representative positions or colors. Sometimes it is more practical to define the transfer functions based on a binary black-white stripe pattern. The transfer function for an equal width black-white periodic pattern is referred to as the contrast transfer function. Examples: equals the OTF of an ideal lens system equals, a perfect lens system will provide a high contrast projection without shifting the periodic pattern, hence the optical transfer function is identical to the modulation transfer function. Typically the contrast will reduce gradually towards zero at a point defined by the resolution of the optics. For example, a perfect, non-aberrated, f/4 optical imaging system used, at the visible wavelength of 500 nanometers, would have the optical transfer function depicted in the right-hand figure. It can be read from the plot that the contrast gradually reduces and reaches zero at the spatial frequency of 500 cycles per millimeter. In other words, the optical resolution of the image projection is 1/500th of a millimeter, or 2 micrometer. Correspondingly, for this particular imaging device, the spokes become more and more blurred towards the center until they merge into a gray, unresolved, disk. Note that sometimes the optical transferred function is given in units of the object or sample space, observation angle, film width, or normalized to the theoretical maximum. Conversion between the two is typically a matter of a multiplication or division. For example, a microscope typically magnifies everything 10 to 100-fold, and a reflex camera will generally demagnify objects at a distance of 5 meters by a factor of 100 to 200. The resolution of a digital imaging device is not only limited by the optics, but also by the number of pixels, more in particular by their separation distance. As explained by the Nyquist-Shannon theorem, to match the optical resolution of the given example, the pixels of each color channel should be separated by 1 micrometer, half the period of 500 cycles per millimeter. A higher number of pixels on the same sensor size will not allow the resolution of finer detail. On the other hand, when the pixel spacing is larger than 1 micrometer, the resolution will be limited by the separation between pixels. Moreover, aliasing may lead to a further reduction of the image fidelity. OTF of an imperfect lens system equals, an imperfect, aberrated imaging system could possess the optical transferred function depicted in the following figure. As the ideal lens system, the contrast reaches zero at the spatial frequency of 500 cycles per millimeter. However, at lower spatial frequencies the contrast is considerably lower than that of a perfect system in the previous example. In fact, the contrast becomes zero on several occasions even for spatial frequencies lower than 500 cycles per millimeter. This explains the gray circular bands in the spoke image shown in the above figure. In between the gray bands, the spokes appear to invert from black to white and vice versa. This is referred to as contrast inversion, directly related to the sign reversal in the real part of the optical transfer function, and represents itself as a shift by half a period for some periodic patterns. While it could be argued that the resolution of both the ideal and the imperfect system is 2I1/4 m, or 500 lpm, it is clear that the images of the latter example are less sharp. A definition of resolution that is more in line with a perceived quality would instead use the spatial frequency at which the first zero occurs, 10I1/4 m, or 100 lpm. Definitions of resolution, even for perfect imaging systems, vary widely. A more complete, unambiguous picture is provided by the optical transfer function. Equals the OTF of an optical system with a non-rotational symmetric aberration equals. Optical systems, and in particular optical aberrations, are not always rotationally symmetric. Periodic patterns that have a different orientation can thus be imaged with different contrast even if their periodicity is the same. Optical transfer function or modulation transferred functions are thus generally two-dimensional functions. The following figures shows the two-dimensional equivalent of the ideal and the imperfect system discussed earlier, next to an optical system with coma, a non-rotational symmetric aberration. Optical transfer functions are not always real-valued. Period patterns can be shifted by any amount, depending on the aberration in the system. This is generally the case with non-rotational symmetric aberrations. The hue of the colors of the surface plots in the above figure indicate phase. It can be seen that, while for the rotational symmetric aberrations the phase is either 0 or I euro and thus the transfer function is real-valued, for the non-rotational symmetric aberration the transfer function has an imaginary component and the phase varies continuously. Practical example, high-definition video system equals, while optical resolution, as commonly used with reference to camera systems, describes only the number of pixels in an image, and hence the potential to show fine detail. The transfer function describes the ability of adjacent pixels to change from black to white in response to patterns of varying spatial frequency, and hence the actual capability to show fine detail, whether with full or reduced contrast. An image reproduced with an optical transfer function that rolls off at high spatial frequencies will appear blurred in everyday language. Taking the example of a current high-definition video system, with 1920 by 1080 pixels, the Nyquist theorem states that it should be possible, in a perfect system, to resolve fully in total of 1920 black and white alternating lines combined, otherwise referred to as a spatial frequency of 1920 halves equals 960 line pairs per picture width, or 960 cycles per picture width. In practice, this is far from the case, and spatial frequencies that approach the Nyquist rate will generally be reproduced with decreasing amplitude, so that fine detail, though it can be seen, is greatly reduced in contrast. This gives rise to the interesting observation that, for example, a standard definition television picture derived from a film scanner that uses oversampling, as described later, may appear sharper than a high-definition picture shot on a camera with a poor modulation transfer function. The two pictures show an interesting difference that is often missed, the former having full contrast on detail up to a certain point but then no really fine detail, while the latter does contain finer detail, but with such reduced contrast as to appear inferior overall. Calculation. Most optical design software has functionality to compute the optical or modulation transfer function of a lens design. Ideal systems such as in the examples here are readily calculated numerically using software such as GNU Octave or MATLAB, and in some specific cases even analytically. The optical transfer function can be calculated following two approaches, as the Fourier transform of the incoherent point spread function, or, as the autocorrelation of the pupil function of the optical system. Mathematically both approaches are equivalent. Numeric calculations are typically most efficiently done via the Fourier transform. However, analytic calculation may be more tractable using the autocorrelation approach. Example Ideal lens system with circular aperture. Autocorrelation of the pupil function since the optical transfer function is the Fourier transform of the point spread function, and the point spread function is the square absolute of the inverse Fourier transformed pupil function, the optical transfer function can also be calculated directly from the pupil function. From the convolution theorem it can be seen that the optical transfer function is in fact the autocorrelation of the pupil function. The pupil function of an ideal optical system with a circular aperture is a disk of unit radius. The optical transfer function of such a system can thus be calculated geometrically from the intersecting area between two identical disks at a distance of, where is the spatial frequency normalized to the highest transmitted frequency. In general the optical transfer function is normalized to a maximum value of 1/4, so the resulting area should be divided by. The intersecting area can be calculated as the sum of that of two identical circular segments, where is the circle segment angle. By substituting, and using the equalities and, the equation for the area can be rewritten as. Hence the normalized optical transfer function is given by. A more detailed discussion can be found in and. Numerical evaluation the one-dimensional optical transfer function can be calculated as the discrete Fourier transform of the line spread function. This data is graphed against the spatial frequency data. In this case, a sixth-order polynomial is fitted to the MTF versus spatial frequency curve to show the trend. The 50% cutoff frequency is determined to yield the corresponding spatial frequency. Thus, the approximate position of best focus of the unit under test is determined from this data. The Fourier transform of the LSF cannot be determined analytically by the following equations. Therefore, the Fourier transform is numerically approximated using the discrete Fourier transform, where the value of the MTF number of data points index term of the LSF data pixel position. The MTF is then plotted against spatial frequency and all relevant data concerning this test can be determined from that graph. Measurement. The optical transfer function is not only useful for the design of optical system, it is also valuable to characterize manufactured systems. Starting from the point spread function The optical transfer function is defined as the Fourier transform of the impulse response of the optical system, also called the point spread function. The optical transfer function is thus readily obtained by first acquiring the image of an incoherent point source, and applying the two-dimensional discrete Fourier transform to the sampled image. Such a point source can, for example, be a bright light behind a screen with a pinhole, a fluorescent or metallic microsphere, or simply a dot painted on a screen. Calculation of the optical transfer function via the point spread function is versatile as it can fully characterize optics with spatial varying and chromatic aberrations by repeating the procedure for various positions and wavelength spectra of the point source. Using extended test objects for spatially invariant optics when the aberrations can be assumed to be spatially invariant. Alternative patterns can be used to determine the optical transfer function such as lines and edges. The corresponding transfer functions are referred to as the line spread function and the edge spread function, respectively. Such extended objects illuminate more pixels in the image, and can improve the measurement accuracy due to the larger signal-to-noise ratio. The optical transfer function is in this case calculated as the two-dimensional discrete Fourier transform of the image and divided by that of the extended object. Typically either a line or a black-white edge is used. The line spread function, the two-dimensional Fourier transform of a line through the origin, is a line orthogonal to it and through the origin. The divisor is thus zero for all but a single dimension. By consequence, the optical transfer function can only be determined for a single dimension using a single line spread function. If necessary, the two-dimensional optical transfer function can be determined by repeating the measurement with lines at various angles. The line spread function can be found using two different methods. It can be found directly from an ideal line approximation provided by a slit test target, or it can be derived from the edge spread function, discussed in the next subsection. The edge spread function, the two-dimensional Fourier transform of an edge, is also only non-zero on a single line, orthogonal to the edge. This function is sometimes referred to as the edge spread function. However, the values on this line are inversely proportional to the distance from the origin. Although the measurement images obtained with this technique illuminate a large area of the camera, this mainly benefits the accuracy at low spatial frequencies. As with the line spread function, each measurement only determines a single axis of the optical transfer function. Repeated measurements are thus necessary if the optical system cannot be assumed to be rotational symmetric. As shown in the right-hand figure, an operator defines a box area encompassing the edge of a knife-edge test target image back illuminated by a blackbody. The box area is defined to be approximately 10% of the total frame area. The image pixel data is translated into a two-dimensional array. The amplitude of each line within the array is normalized and averaged. This yields the edge spread function, where ESF equals the output array of normalized pixel intensity data, equals the input array of pixel intensity data, equals the ith element of, equals the average value of the pixel intensity data, equals the standard deviation of the pixel intensity data, equals number of pixels used in average. The line spread function is identical to the first derivative of the edge spread function, which is differentiated using numerical methods. In case it is more practical to measure the edge spread function, one can determine the line spread function as follows. Typically the ESF is only known at discrete points, so the LSF is numerically approximated using the finite difference, where equals the index, equals position of the pixel, equals ESF of the pixel. Using a grid of black and white lines, although sharpness is often judged on grid patterns of alternate black and white lines, it should strictly be measured using a sine wave variation from black to white. Where a square wave pattern is used, not only is there more risk of aliasing, but account must be taken of the fact that the fundamental component of a square wave is higher than the amplitude of the square wave itself. A square wave test chart will therefore show optimistic results. The square wave result is sometimes referred to as the contrast transfer function. Factors affecting MTF in typical camera systems. In practice, Many factors result in considerable blurring of a reproduced image, such that patterns with spatial frequency just below the Nyquist rate may not even be visible, and the finest patterns can appear washed out as shades of gray, not black and white. A major factor is usually the impossibility of making the perfect brick wall optical filter. Such a filter is necessary to reduce aliasing by eliminating spatial frequencies above the Nyquist rate of the display. Digital inversion of the optical transfer function. Often the contrast decreases significantly before the Nyquist frequency of the display is reached. Digital image deconvolution is the procedure that reverses the contrast reduction to yield a sharper image. Errors in the recording due to noise or aliasing will also be amplified. The technique is thus only effective on high-quality, high signal-to-noise ratio recordings. Oversampling and downconversion to maintain the optical transfer function equals. The only way in practice to approach the theoretical sharpness possible in a digital imaging system such as a camera is to use more pixels in the camera's sensor than samples in the final image, and downconvert or interpolate using special digital processing which cuts off high frequencies above the Nyquist rate to avoid aliasing whilst maintaining a reasonably flat MTF up to that frequency. This approach was first taken in the 1970s when flying spot scanners, and later CCD line scanners, were developed which sampled more pixels than were needed and then downconverted, which is why movies have always looked sharper on television than other material shot with a video camera. The only theoretically correct way to interpolate or downconvert is by use of a steep low-pass spatial filter, realized by convolution with a two-dimensional sin, x/x weighting function which requires powerful processing. In practice, various mathematical approximations to this are used to reduce the processing requirement. These approximations are now implemented widely in video editing systems and in image processing programs such as Photoshop. Just as standard definition video with a flat MTF is only possible with oversampling, so HD television with full theoretical sharpness is only possible by starting with a camera that has at least twice as many pixels, and then digitally filtering. With movies now being shot in 4K and even 8K video for the cinema, using cameras like the Red, we can expect to see the best pictures on HD TV only from movies or material shot at the highest standard. However much we raise the number of pixels used in cameras, this will always remain true, and the same problem exists of course with stills cameras, where a better image can be expected when, say, a 10 megapixel image is converted to a 5 megapixel image, than could ever be obtained from an even the best 5 megapixel camera. Because of this problem of maintaining a flat MTF, broadcasters like the BBC did for a long time consider maintaining standard definition television, but improving its quality by shooting and viewing with many more pixels. Another factor in digital cameras and camcorders is lens resolution. A lens may be said to resolve 1920 horizontal lines, but this does not mean that it does so with full modulation from black to white. The modulation transfer function gives the true measure of lens performance, and is represented by a graph of amplitude against spatial frequency. Lens aperture diffraction also limits MTF. Whilst reducing the aperture of a lens usually reduces aberrations and hence improves the flatness of the MTF, there is an optimum aperture for any lens and image sensor size beyond which smaller apertures reduce resolution because of diffraction, which spreads light across the image sensor. This was hardly a problem in the days of plate cameras and even 35mm film, but has become an insurmountable limitation with the very small format sensors used in digital cameras and especially video cameras. First-generation HD consumer camcorders used 1/4-inch sensors, for which apertures smaller than about f4 begin to limit resolution. Even professional video cameras mostly use 2/3-inch sensors, prohibiting the use of apertures around f16 that would have been considered normal for film formats. Certain cameras feature an MTF auto-exposure mode, where the choice of aperture is optimized for maximum sharpness. Typically this means somewhere in the middle of the aperture range. Trend to large format DSLRs and improved MTF potential there has recently been a shift towards the use of large image format digital single-lens reflex cameras driven by the need for low light sensitivity and narrow depth of field effects. This has led to such cameras becoming preferred by some film and television program makers over even professional HD video cameras, because of their filmic potential. In theory, the use of cameras with 16 and 21 megapixel sensors offers the possibility of almost perfect sharpness by down conversion within the camera, with digital filtering to eliminate aliasing. In practice, such cameras currently fail in this respect, and they do not have the processing power to do what is required. The Canon EOS 5D Mark II is believed to use only every third line, and hence suffers bad aliasing, as its optical filter is optimized for stills use. The Panasonic Lumix DMC GH2 may do some processing across pixels, producing very sharp images, but with some aliasing. Nevertheless, such cameras produce very impressive results, and appear to be leading the way in video production towards large-format down conversion, with digital filtering becoming the standard approach to the realization of a flat MTF with true freedom from aliasing. Limitations: in general, the point spread function, the image of a point source, also depends on factors such as the wavelength and field angle. When such variation is sufficiently gradual, the optical system could be characterized by a set of optical transfer functions. However, when the image of the point source changes abruptly upon lateral translation, the optical transfer function does not describe the optical system accurately. See also, transfer function, signal transfer function, optical resolution, signal-to-noise ratio, Strehl ratio, wavefront coding, bokeh, minimum resolvable contrast, minimum resolvable temperature difference. References. External links: Modulation Transfer Function, by Glenn D. Borman on SPIE Optopedia. How to Measure MTF and Other Properties of Lenses, by Opticos Corporation.